talk about something which is not normally considered to be a subject of very deep and rich science, and this is what is called as public health. So, public health to many is considered to be an activity of building toilets, etc., but one also has to recognize that public health is one of the major challenges of the underserved community. While public health happens to be important, diagnostics for the purpose of public health remains to be a backbone of what public health is all about. By diagnostics, we normally consider either some body signals or body images or dealing with some body fluids for analysis. This is what we normally call as diagnostics. So, today I will discuss that how can you bring in perspectives of computational pathology in the domain of public health and have its intervention through diagnostic procedures. So, if you recall or if you recognize, if you consider India as a model country, but there could be many other countries of similar model. I am talking about any country which is having some underserved community. That means a community which is not well served. In this community, a major fraction of the population lives in rural areas, but they are deprived of basic healthcare facilities. Why they are deprived of basic healthcare facilities? Majority of the hospitals and healthcare centers is skewed in the urban location. Otherwise, even if there are some healthcare facilities in the rural place, they do not get doctors, they do not get technicians. If they go for a diagnostic test, there is a large delay between giving the sample and getting the result. Cost is a prohibitive factor. So, keeping all these factors into account, the healthcare solution for the underprivileged community is quite dismal. Now, I will show you that in a very simple way how this problem can be addressed and where diagnostics comes into the picture. One of our collaborators, Dr. Shatadal Saha, his photograph is shown here. By training he is an FRCS doctor, but his main activity is medical entrepreneurship. He is also currently a professor at the School of Medical Science and Technology, IIT Kharagpur, but beyond that, he actually facilitates building up of small infrastructure which we may call as health kiosk just for our own purpose, which act as backbones for rural healthcare. So, what happens? A patient approaches this small place which is like a small brick and mortar room, and the patient interfaces with a health worker who in this case is a minimally trained girl. The health worker is not a trained nurse or a trained technician, but a minimally trained girl. She is not even class 10 educated, but she has already gone through a training procedure by which she can collect medical data from the patient, transfer that data to a software which is a medical algorithm based software, and also the health worker can make certain basic measurements, like can record the height, weight, blood pressure, these kinds of things. Then once this data is interfaced with the doctor who is sitting in the big city, that doctor looks into this medical record and then through voice over internet protocol discusses the case with the patient on a one-to-one basis, because there will be many issues which the doctor has to clarify from the patient and patient has to explain directly to the doctor. Everything is not the job of the health worker. And then this result is basically analyzed. This result, by result I mean the outcome of this discussion and the medical software based information, it is being analyzed, and the doctor in this way gives a recommendation after the analysis. So the recommendation can be medicines or the recommendation can be diagnostics. Diagnostics will require further pathological intervention. So this model has an extremely influential socio-economic perspective. It has a model which is empowered by rural women. It is having a knowledge base which is medical algorithm based software. It is having a technology which is low cost communication and diagnostics. It has, it offers a service, it promotes public health and education, and also it has a business model. For example, the patient has to pay a particular amount, say currently 60 Indian rupees for every 2 visits with any number of reportings in between. So it has a business model. Now on the face it looks good, but if you see at the end there is a bottleneck. So this health kiosk has an element of training which is given to the local girls, that is there. Software is there, of course it is continuously being improved through machine learning and other capabilities, so that the software becomes almost like a humanoid type of thing, I mean almost like a doctor. Connectivity is of course nowadays much better. Connectivity, by connectivity I mean internet connectivity. Business model exists, but diagnostics is the bottleneck. So when the patient is told that you have to do these diagnostic tests and these will cost this much, from our experience we have seen that a majority of the patient, they just run away and they never participate in the follow up. So for example, somebody who is having diabetes is never detected. So the person terminates in the form of at the end some cardiac or neurological or kidney disorder, which is a tertiary healthcare problem originated out of the continuous high level of blood glucose. So this is very common, and non-availability of infrastructure or large time gap between test and results, inaccuracy due to sample transportation, all these factors actually accumulate to these challenges. So clearly the kind of pathology that we imagine, we have to realize that that pathology will not work here. All of you have come here to do a course of computational pathology, and computational pathology appears to be a very white colored type of activity, but we have to understand that one of the backbones of computational pathology, what we are imagining is a pathological activity which is done in a nice sophisticated lab under a very controlled environment. I am not talking about that pathology. So, it is an alternative pathology for which alternative way of looking into computational pathology is required. So, this is not the traditional computational pathology that you will hear about maybe in the remaining lectures of this course. So, what is the pathology about? I will give an example of testing of blood, which is a blood test is one of the very common pathological tests. So, what you do here is instead of puncturing your vein, you prick the finger and take one drop of blood out of it. That one drop of blood is loaded in a device, which I will explain what kind of device it is, because the computation depends on the device. And then there is a chemical which is there in the device. I am trying to simplify it to give it on a conceptual scale, and then I will get into the details. There is some chemical which on reacting with blood will change color, and the change in color has of course a qualitative perspective, that is visual change in color that you can clearly see, but by that you cannot give a quantitative answer. So, if you want a qualitative answer, yes or no, for example, a pregnancy test kit, right, you can, the pregnancy test kit can give an answer whether the pregnancy is positive or negative. You do not expect an answer of 1 unit pregnancy, 2 unit pregnancy like that. But when you go for a blood glucose measurement, it is a quantified, right. It is not a question of whether the blood has glucose or not. Question is what is the concentration of the glucose. So, the whole idea is that how do you convert this color signal into a quantitative analytics, and that is where actually a whole lot of computation may be involved. So, if that is done and if all those computation actually can be done in a smartphone, then you take an image of the color signal, do an analytics of the image maybe using the Android platform of the smartphone, and then display the result there itself. So, this advantage is that this is called as lab on a chip, or in this case lab on a paper, a piece of paper. So, instead of bringing the patient to the hospital, you can make a small handheld device which you can bring to the patient and do all the analysis here. This is inexpensive, it does not require too much of infrastructure, the result is rapid and it can be automated. While automation is not always necessary, but if required, large numbers of these tests can be done in an automated environment. But it is easier said than done. So many companies or so many, I would say, research labs, it may be companies or academic institutes, they have engaged for a long time in developing such devices, and fantastic results are obtained in the lab. But you will see that only a very small fraction of this is actually translated into practice, which is used by doctors. So, where is the challenge? The challenge is when you bring out your technology from the lab and bring it to the field, there are certain additional factors. You do not have a very stable supply of power which you get in the lab. In the lab we have air conditioned environment, the chemicals are stored in the refrigerator. In the field if you go, you will see extreme dirt, dust, humidity, and no refrigeration is possible beyond you can carry an ice box and keep it cool for some point of time. Supply chain model for this kind of diagnostics does not exist. You do not get skilled technicians who can draw blood from the vein and who can do analysis with blood using a pathology framework, so you have to rely more on human interference with less training, and therefore you may have to bring in more computation to supplement that. And cost wise it is very sensitive. While you add more sophistication, the cost will go up, and in that case people will not accept that diagnostics. So, one of the first key steps is to have a simple platform which is like a piece of paper on which you can do the diagnostics. Paper is one of the most commonly used platforms, and the advantage of paper is the capillary flow on the paper. By capillary action or surface tension force, if you drop a drop of blood or any fluid as such, you will find that it spreads diffusively. So, if there is a chemical, now you can expose that blood to that chemical and it can show a change in color. You do not require a separate pumping to do this. The problem is that if you allow the blood to just be put on the paper and get spread, then all what happens is that the blood will spread randomly instead of going to a targeted spot where the reaction is to be done. But if you want to have the blood test on a targeted spot, the advantage is that you can focus your mobile camera and everything, you can illuminate that spot, you can focus your mobile camera and do all the image analytics there. Not only that, you can have many such targeted spots, and at each spot you can do one test. So, a large number of tests can be done simultaneously. In paper it is not so easy to do, because if you take a scanning electron microscopy image of a paper, you will see that the cellulose fibers which are shown here, they are absolutely random and interconnected, and how fluid flows through such paper. So, this is a sort of example where you can clearly see that the velocity vectors are randomly distributed all around. So, we do not want this eventually if you want to bring the blood from a source to a destination. So, something like this where you load the blood here, you transport the blood from here by capillary action to here where the reactants are kept. So, in this way you have to block these transverse passages, and for that you have to create something called as hydrophobic barrier. That means a barrier which has a phobia for watery type of fluid, and that will block the flow. So, question is how this blocking is possible. You have to make a structure of the channel or the hydrophobic barrier so that there is no flow across and only longitudinal flow of blood takes place. In the literature, there are many techniques which do that, but the problem is they are expensive. Imagine, see, I started with a basic motto, and no matter whether it is experimental pathology or computational pathology or actually in practice a combination of both, we should keep our focus that we cannot make a cost, we cannot lead to a cost which is prohibitive for use by people who represent the underserved community. That kind of device will not work for this purpose. And we have to understand this very clearly, that the design of the method and the design of the entire device should be according to that. So, one of my former PhD students, Dr. Shantimoy Kaur, he came up with this idea. So, he said, or he did it in practice, that you just make a design of this channel in any softwares, even you can do it in an office software, and then print this design in a piece of paper, which is of course not the ordinary paper, but the paper on which you are doing the diagnostic test. So it is either a filter paper or a nitrocellulose paper, which has more organized fiber structure than the regular paper. You make a print of this on both sides of the paper. Why on both sides of the paper? Because paper is actually a 3-dimensional structure. So if you load blood on one side and on other side there is no channel, then the blood will leak. But just by printing, the channel is not made. The next magic step is something like this, that you heat this piece of paper on a hot plate at 200 degrees centigrade for about 4 to 5 minutes. Once you do that, the toner particles which come from the printer, they melt and block the pores, and that is how the hydrophobic barriers are created. So this, I have gone through many processes of making microchannels, but this is like a zero cost microchannel fabrication. You don't require a lab actually to do it. You can sit in an office and make microchannels on a piece of paper. It looks simple. I thought that I will put very less number of mathematics and equations in my talk, because this is a general talk, but because it is computational pathology, the next obvious step will be that when we make this channel and when the analyte is flowing, it may be a chemical or blood or a chemical in a blood, whatever, how do you optimize that flow? How do you know that what is that flow rate, what is that pressure drop, what is the concentration of the analyte? All these things have to be optimized, and to do that you have to do a fluid flow simulation. So the fluid flow simulation is essentially that you have to know what is the velocity field in the channel. For that you have to simulate using a technique called as computational fluid dynamics, or CFD, to get the velocity field. Once you get the velocity field, so Ux and Uy say are the velocity components along x and y direction, then you solve another equation. This also you solve by computer simulation. It is called as species transport equation or mass transfer equation. So if there is a solute that is being carried by the fluid, that transport, the concentration of the solute is given by this C, and D is the diffusion coefficient. Where it is so interesting is that, first of all, if you normalize this, that means if you normalize the strength of fluid flow with respect to the strength of diffusion, you come up with a non-dimensional number which is called as Peclet number, PE. Where it is, yes. So this is basically the ratio of advection by diffusion. So depending on the strength of fluid flow, this number will vary, and you will get a non-dimensional governing equation where it is coupled with the chemistry, and this is so interesting, is that at an interface between the fluid and the solid, either at the boundary wall or at a reservoir, you have a chemical reaction. The chemical reaction has an association and dissociation constant. These rate constants are themselves functions of fluid flow, and this you do not know a priori. So you have a complex coupling between reaction, fluid flow and diffusion, and this entire thing is so strongly coupled that without doing computer simulation you actually do not know that how they are related. And also very importantly, it is a function of the height of the channel. So all these things make it quite involved, and this is one aspect of computational pathology, simulating the transport, fluid flow and species transport in a situation where you are dealing with body fluids. And that, so this is one of the, this nobody will teach you in traditional computational pathology, because this kind of situation in a traditional pathology lab doesn't exist. But when you have a new pathological model, you should have a computational pathological paradigm which is consistent with this new pathological model. So I will give you an example where this kind of diffusion is important. So in blood testing, one of the key requirements is the separation of plasma from the whole blood. If you see the report of blood glucose, if some of you or maybe all of you are very young, but your parents, grandparents, they may be routinely doing the plasma glucose test. So the blood sugar test in the normal language. So you will see that the result that is given is plasma glucose level, not the whole blood. So there are reasons. One is the chemistry of the test demands plasma itself, not the whole blood. There are other more practical reasons. When you do a colorimetric assay, then the deep red color of the red blood cells can interfere with the colorimetric signaling. So you get rid of that. That is one practical aspect. And the third aspect is that even from medical standards, the plasma glucose is considered to be a benchmark data for finding out the treatment protocol, not the whole blood glucose. So this is the device which is called as H filter. This is made by folding of a piece of paper in a Japanese folding style called as origami. So this doesn't require any manufacturing, zero cost filter. So here comes a phosphate buffer solution and here comes the blood sample. By using the enhanced diffusion of glucose or sugar molecules in plasma as compared to the whole blood, the entire plasma gets pulled up and it gets separated over a length. What is this magic length? For that you have to do computation. You have to study the fluid flow, mass transfer, all these equations to come up with an optimal length at which this entire plasma gets separated. This is one of the design problems in computational pathology. Had this been a longer course, I would have shown you that how actually you can work with this design problem in hand. But because it is a short course, I cannot elaborate more. But I am just giving you an idea how these design problems actually help in developing medical devices. Okay. So this is now when you have a real plasma glucose detection, so you have a first step which is plasma separation, and then you have a colorimetric reaction involving plasma. So that reaction is done in this pad. So this black strip is like a paper strip. You load the blood sample here, and instead of using the H filter, we are using a membrane filter to separate the plasma goes here, and then the plasma takes part in certain reaction. What reaction? Normally we use an enzyme called as glucose oxidase. Along with that there is peroxidase, potassium iodide, etc. So glucose oxidase acts as a catalyst and catalyzes the dissociation of glucose in the presence of water and oxygen to produce hydrogen peroxide. And hydrogen peroxide takes part in a side reaction. It reacts with potassium iodide to produce iodine, which gives a reddish brown color. So this is the qualitative part of it. Where is the quantitative analytics? So this is what you will learn in chemistry books. Even in junior high class you can learn it. Question is, where is the quantitative aspect where computation comes? So I will give you one first very simple thing, which is like curve fitting and data interpolation. When we were students, it was known as curve fitting data interpolation. Now it is being given a very sophisticated name, one aspect of machine learning. So I mean days change, you know, the same things come in a new name with a new hype, with a new hope for everybody to earn their livings. So when I was a student of class 11, I learned a chapter in statistics called as correlation and regression, and I still consider to be one of the very important chapters. So now, so what you do is essentially you get the glucose concentration from the lab. So when you do the test, in the lab you do a gold standard or the classical test which is done by the regular pathologists to get that result. And then you make a grayscale intensity image analysis of the image that you are doing in your device, and then you make a curve fitting. So then what you do is, this is called as training of data. Your system must have a training so that given an unknown sample, from the intensity you can read a glucose concentration. But when you read the glucose concentration from the intensity, this is where comes your validation. How do you know that that result is actually good? So in that case, then you compare it with the laboratory data and see what is the difference. Using this difference, you refine this regression curve, and this is one of the hallmarks of machine learning, and that is how you can actually embed machine learning in microfluidics based device analytics. So how do we improve the design and predictive capability of these kinds of devices using computational pathology? So I have classified two clear-cut, possibilities. One is optimization of the chemical reaction by simulation. For example, you say that I use X volume of blood and I use Y volume of chemical. Now how do you know what is this X and Y? To give you the best possible stoichiometry and the output signal at the shortest time. So for that, you have to play with the stoichiometry, homogeneity, reaction rate, transport. As I told you, this reaction and fluid flow, mass transfer, they are all coupled. So there is one aspect of computational pathology. This is a new aspect, and anybody who is coming in new into computational pathology should adopt this as a new branch of research. This is something which is going to start, and it is going to make a big impact in the market. The other is already known, which is image processing and machine learning. So this is of course required, this is of course very well known, but this has been a traditional understanding of what is required. So you have a pre-processing, features of optimization and refinement of the calibration curve. So all these things actually require aspects of image analytics and machine learning. So on one side you see what is the knowledge base of a computational pathologist should be. On one side this reaction, transport, kinetics, fluid flow. On another side image analytics, machine learning. So all these together actually form the gamut of computational pathology which is required for new generation medical devices. So I am giving you an example. So you can see these are the stoichiometric reactions that I have just talked about. The reaction of glucose with water and oxygen to produce hydrogen peroxide, and that reaction with potassium iodide to iodine. So if you now transfer it into a design problem of a student class, let X microliter of blood have C numbers of glucose molecules. Y numbers of glucose oxidase molecules are required for complete reaction. Question is, what is the optimal value of Y under the flow conditions? This optimal value is not what you read from the chemistry book. The reason is that real-time reaction has many issues such as improper mixing. See, if you want a reaction, first two samples should mix properly and then they will react. So improper mixing, incomplete and slow reaction, etc. The other aspect is you have to use some error minimization principles towards your design optimization. And a model has to be developed by considering all these, and remember that the best model is that which gives the best agreement with the gold standard. That means what is done in real pathological practice. Example for image analytics, if it's a cancer analysis, then your gold standard is biopsy. So whatever prediction agrees the best with the biopsy, that is the best acceptable model. So computational image analytics, this is of course sort of very well developed subject, and it is growing and it is going to grow. So there are many issues in colorimetric detection using a smartphone, where you can do computation and make the study. For example, effect of illumination. What is the background illumination in which you are taking the image using the smartphone? Camera properties vary from brand to brand. So I prepare a calibration curve with certain camera and all those things. You use the same mobile app but in a different, so you download it from the app store and then you apply that for a problem or for a mobile phone where the camera setting is completely different. How do you normalize this? This is the open research question. So possible solutions by image processing use color balance or color correction algorithms. This is one of the very hot topics in computational pathology. Color space based invariant feature extraction, mapping of the color features to obtain diagnostic results. So this mapping also has to be done very precise. Machine learning for refinement of the calibration data, I have already discussed that you already have a regression, but how to use machine learning to improve the quantitative capabilities. Every new data you study is like a gold mine, because using that you can continuously improve your prediction, so that in the next, from the next result onwards, you see better and better predictive capabilities. The next case study that I will show is that by using all these, we have developed certain devices, and I can show you how these devices work. So this is a device for hemoglobin detection. Hemoglobin is one of the key parameters that is very, very important for maternal and child health, nutrition, or in general any diseased condition. So question is that, do you have a robust way of finding out the concentration of hemoglobin? Nowadays you will see that there is a whole lot of hype in non-invasive hemoglobin detection, and one has to be very careful about it. I have talked with many doctors, and the general understanding is that you can draw a correlation of something with something, but it doesn't come from a consistent physics or physiology. So hemoglobin is a chemical constituent that comes chemically from blood. Now by looking into your eye color or skin color or eyelid color, or taking an image, it may be possible to sometimes clinically detect it, but sometimes you may become a fool. For example, out of sheer tension, stress, etc., you may become reddish. And then if image is done and analytics is done, whatever is 4 level of hemoglobin will come as 15 level of hemoglobin. So all this is good, because companies want to make business. So whether the business is scientifically consistent with what is the requirement by pathology is something that has to be seen. So there is no substitute of doing a blood test while you are obtaining the hemoglobin data. So when you want to do that, you have to keep in mind that when you expect your answers to be very good, you expect your answers to be very good when you actually follow the gold standard protocol, which is followed in the lab but in a miniaturized form. So that is what is done here. there is a chemical called as Drapkin solution which is used by pathology labs. You go to any blood pathology lab, you will see Drapkin solution is there. They purchase it in bulk. So if the blood is exposed to the Drapkin solution, then what happens? Then the red blood cells are lysed and it brings out the hemoglobin out of the RBCs. This is called as cyanomethylglobin, the hemoglobin that comes out of the lysis of the red blood cells. So this hemoglobin, it acts as a catalyst. It catalyzes the dissociation of hydrogen peroxide, which is another chemical used here, so that hydrogen peroxide is dissociated into hydrogen and oxygen. And this oxygen is used to oxidize, in this case a chemical called as O-toluidine, because that oxidation produces a very discernible bluish green color, and that can be imaged and analysis can be done. So you can see the reaction kinetics curve of this hemoglobin detection, because here also I want to give you another example where computational pathology aspect becomes important. So H2O2 will decompose into water and nascent oxygen, and that will react with O-toluidine to produce a chemical which gives a bluish green colorimetric signal. So if you plot the intensity as a function of time when this color develops, you will see that for different concentrations, the intensity peaks are obtained differently. So question is that this is based on a particular reagent volume for a given hemoglobin. So this is the hemoglobin content. So starting from 2.5 milligram per deciliter, gram per deciliter to 15.1 gram per deciliter. So the question is that with this widely varying range, you have a widely varying time at which the reaction curve saturates, and it all depends on how much chemical you have added for the reaction. So every time you cannot actually do a trial and error to make sure that you get the peak reached or the saturation reached at the shortest time, because the time at which the saturation is reached, that is the earliest time by which your diagnostic test is complete. So shorter that time is, that means more rapid the diagnostics. So this time is a function of the volume of chemicals that you add, and how they are related. All these trials and errors, instead of doing it experimentally, one can do it by computational pathology. A similar colorimetric signal example I will talk about. This is a case called evaluating antibiotic resistance. This is one of the very challenging problems in the modern civilization, that when an antibiotic is administered, the antibiotic does not work. Why it does not work? Maybe at a young age the child had an overuse of antibiotic for which the body has created a resistance, or the antibiotic has been abused, that means the antibiotic has been used but the course has not been completed. So when the fever goes away, the parents are happy and they are not completing the course. Sometimes it has an economic perspective. Sometimes even if the patient knows that the course has to be completed, the patient, just because the cost of the antibiotic, doesn't go for further medication, because the patient thinks that cure has taken place. Sometimes the bacteria themselves have evolved in a way with time that they can now beat the medicine, and this is a very dangerous condition. So before treating a patient, a doctor must know whether an antibiotic will work or not, because in a life threatening infection, every 1 hour is critical, even every 1 second is critical. So to do that, one has to assess whether an antibiotic will work or not. So this is a simple folded paper device which has been developed in our group. So there are 4 layers. One layer is a base, another layer contains the bacterial suspension, in this case E. coli cultured from urine sample, then an antibiotic, and then a colored chemical called as chromogen, which is originally blue in color. So now you fold this paper so that the antibiotic comes in contact with the bacterial suspension. Once they come in contact, if there is successful killing of bacteria with antibiotic, this chromogen will start changing its color from blue to pink. And by making a colorimetric analysis of this image, so all the examples, these examples will appear to be very different, glucose, hemoglobin, antibiotic resistance, but all these essentially depend on a very accurate and efficient quantitative colorimetric analytics. And that is where a whole lot of computation can come into the picture. Now you have a piece of paper in which you do all these diagnostics. But how the blood is flowing on this paper? The blood is flowing on this paper by capillary action, surface tension driven flow. How can you speed up this? One possibility is to use electric field, because the cellulose fibers which constitute the paper, they have a negative zeta potential because of the carboxylic acid group. So if you apply an electric field because of the surface charge, the fluid will move faster. Question is, how do you now apply the electric field? You have to embed some electrodes on the paper. That will add to the cost of the device. So I discussed with some of my students, former students, and we came up with a solution which is very simple and unique. Instead of making electrodes on a paper, I just told my students that you make sketches of pencil using HB pencil, and the graphite that is there in the lead of the pencil, that when deposited on the paper acted as an electrode. So you have a simple piece of paper on which you have printed channels and you make pencil sketches. These things are normally done by school students, and this is how you can innovate a microfluidic device which is called as paper and pencil microfluidic device. It started with an all new branch of paper and microfluidics from our lab at IIT Kharagpur, and now many groups in the world are actually using this technique. So using this paper and pencil microfluidics, we have seen how it is possible to do multiple tests with single drop of blood. So you have one drop of blood and in the source, one part will go to this B where bilirubin is detected, another part will go to G where glucose is detected, concentration. So I am not getting into the chemistries, but what will be the voltages across these two and these two, so that at the shortest time you get the accurate signal. That you have to do by computation, that you have to optimize by computation. So every medical device is coming up with an optimization problem which can best be addressed by computational pathology. So I will try to conclude with a couple of more slides, and the first one discusses about how you bring this technology from the lab to outside the lab. So this is a place called as Shalboni, which is about 1 hour drive from Kharagpur, and in Shalboni there is a hospital which is now being managed by a private body which is led by Dr. Shatadol Saha. Therefore we could arrange for doing some validation tests. Why these validation tests are so critical? Because the place where we did the test, you do not have a controlled environment where you have dirt free, dust free, humidity controlled, air conditioned, not like that. So what kind of environment? You can see here that there is a table, we got hold of this table. So this is Dr. Saha and my students and me, we were all there to do the test. This was done, if I remember correctly, around the month of April in the last year. And then uh, we did find out the findings from our device as compared to the findings from the laboratory gold standard, and that is how we came up with a kind of validation where the validation for the first time has been done in an environment which is different from our own lab. So I will run a small movie. So this will give you some kind of idea about the hospital. I mean, it's a reasonably neat and clean hospital. So these are the paper strips that I am talking about. So a plastic on which you stick the paper and then you load the blood sample and do the analysis. So this is like a credit card for a credit card reader. Just like the credit card is inserted into a credit card reader, this is inserted into a plastic box which is a smartphone reader. So you can see how the plasma is separated. So this is now inserted into the plastic box, and then on the top of this is the smartphone. So there is a mobile app which has been developed by my students and in collaboration with my startup company, and this gives the result of the test immediately. Now we wanted to go beyond this. At least we got an hospital at which we did this analytics. But in reality, rural India or underserved community in the entire world is different. You will see places where there are no doctors. Forget about hospitals. So we chose a place called as Barra in the Birbhum district of West Bengal, and we managed to convince one primary school headmaster who was generous enough to give the space of the ground floor of the building to do the diagnostic tests. So we went with our team, and I will run a small video. There is some sound in this video. I am not sure whether the sound will work from my computer. So these are women who have never done diagnostic tests in their life. Professor Amitava Ghosh, who is the former director of IIT Kharagpur, he is originally from this village actually where we have done this test. So everything is written in the local language, Bengali in this case. You have to understand the perspective, right? This we are not doing for a very sophisticated audience. So they must understand what we are doing. So the patient comes and registers. All these girls are actually local girls, not class 10 pass, but they now are empowered to do all these activities. So they register these patients, and these patients, many of them actually do not have much skill of reading and writing. So they are given paper sheets with two color codes, one color code for glucose, another for hemoglobin. So they will just present that color code to our student, and the student will recognize for what test he or she has come. So I have found these local rural human resources, maybe women, maybe men, they are amazing. In our labs, we give training to students to how to use pipettes, right? So these people almost overnight learned how to use pipettes. So they are amazingly smart, they just have to empower. Most of us underestimate this human resource, and this human resource is one of the greatest strengths of our country. So I will not extend this movie anymore, because the whole idea was to give you a glimpse of what is happening. But I will present a bit more on what we intended to do there. So there was a device called as HemoQ, which is the most widely accepted device for point of care test of hemoglobin. The device costs around 60,000 Indian rupees, and every strip costs 50 Indian rupees. So we tried to compare our results from the HemoQ and see that how our tests were performing. So you can see this, hemoglobin level vis-a-vis the HemoQ standard, which is the blue line. Our results have done exceedingly well. This blue line is a curve fitting of this data, and you can see that hemoglobin level from the hematology analyzer, and this is hemoglobin level from the POC device. This angle is almost 45 degree, this correlation. So it shows that this data scattered around, if we fit it in a curve, that curve gives almost an agreeable correlation between the hematology analyzer hemoglobin prediction and the point of care hemoglobin prediction. So what is the way forward? So using this model, we can form a village health hub which can give access to health care for everybody in the village. It can give home care for vulnerables. It can generate entrepreneurship, employment, etc. And from the purpose of education and research, it can connect health education, deep science and public health. This is a connectivity which is very strongly missing. So the underserved community may adopt the model and replace the existing facilities with this kind of technology enabled low cost system. And computational pathology may work as a backbone towards design optimization of these kinds of new generation medical devices. Still, there are many open scientific issues and questions, because there are many students here who can take up research in the future. I just don't want to stop here by saying what we have done, but possibly what could be done more, and what are the future scopes of work and research. Optimized sample volumes for a given assay. So for a given assay, how much blood, how much chemicals, how much all these are required. Universal connectivity between transport and reaction. On one side there is a fluid flow, on another side there is a chemical reaction. What is the connectivity between that? This physics in terms of a universal picture is not well known. Optimizing the flow design in complex interconnected fibrous porous network. Like the paper is a very complex medium. So how to optimize flow in a paper? Disease modeling on a chip. today, because of interest of time, I did not show you another very interesting work which we call as tumor on a chip. So, using this kind of microfluidic chips, we make a model which mimics tumor metastasis, and that actually, so this kind of paper based microfluidic platforms or PDMS microfluidic platforms or any other microfluidic platforms can actually give rise to very nice modeling of functionality of what happens in a human body in an artificial engineered chip, and for that lots of computation is required to design that chip. AI enabled image analytics for improved quantitative prediction of test results. So, that is where artificial intelligence, machine learning, image analytics and microfluidics all can converge together. And I will end up with the same statement with which I started in the beginning: deep science interfacing public health towards health for a billion. So, this is very, very important, where we have to recognize that public health is not just about making toilets. There is a deep science that comes into delivery of public health model, and that should be interfaced with the societal, economic and other activities to make sure that this model becomes a functional success. So, I would like to acknowledge my collaborators. I do not want to go through individual names, but they are already there: collaborators, former PhD students, present PhD students, present master students and some of the present undergraduate students. You can understand this is a team effort, and all of us have to work together in a coherent fashion to make this a success. And these kinds of activities we do very regularly. For example, tomorrow we are going for a field work in a place called as Balpai, which is very close to this place, but there we are going to implement these devices and see how these devices are working. I would like to acknowledge the funding agencies, primarily funding agencies from the Government of India, and also funding agencies outside India, including the Royal Academy of Engineering, United Kingdom, who have generously funded various parts of this project so that we could come to this stage. Thank you very much.